Hello. 0.31.
Hello? Sorry?
I got 318.31.
Yeah, 318 will do nicely, Ben. Yeah.
Okay.
So therefore, how do I calculate? So we want that's XC, which is effectively ZC. Yep. So ZC dash is equal to, how do we calculate that, gents?
That'll be A squared times ZC.
Yeah. So we're talking about a fifth squared times 318 equals.
I got 12.72 for that.
Yeah, 12.7 will do fine. That's what I've got in my solution. Ohms, yeah?
Yep.
Okay. And then part B is asking us what is the capacitance value seen by the generator. Yeah. So what we could write is ZC dash is equal to 1 over 2 pi F C dash. Yeah.
Yep.
Therefore, we can say that C dash is equal to 1 over 2 pi F Z dash. Follow that, everyone?
Yep. I got 250 micro.
Yeah. 250 microfarads. Yeah. So this step up transformer will make this capacitor look 25 times bigger in terms of farads than it actually is.
Yeah.
Yeah. Right, Ben?
Yeah, fine.
Yeah. Lewis?
Uh-huh.
Warren?
Yep.
Good, good. Right. Now we'll take a look. Solvent transformer problems by shifting impedances. All right. So what we're going to look at here is if we've got a problem like the one at the top there, where we've got a series impedance on the primary side. This is kind of preempting some of the calculations we'll want to do for the real transformer model. And then we've got 3 impedances connected to the secondary side. Yeah. If we had a problem like that, just let me look at the next page in my notes where I give them some values. Not on that one, no. if we wanted to solve this problem, just go through the method. What we do is so here's a method to solve that for any unknowns, as we could, one, shift Z2 to primary, yeah, where Z2 dash is equal to A squared Z2, yeah. Secondly, shift Z3 to primary, where Z3 dash is equal to A squared Z3. And thirdly, shift Z4 to primary, where Z4 dash is equal to A squared Z4. So in other words, we shift all of the secondary side components over to the primary and make them whatever their value is dash by multiplying by the transformer ratio squared. Yeah.
Mike, just quickly, I'm just going to turn my router on and off because it's playing up again. You're going all laggy.
Okay. Okay. Let us know when you're back.
All right, no worries.
Right. So, as I'll put on the right-hand side of the page here, you can also shift E2 to the primary to get E2 dash, shift the three currents, I2, I3 and I4 to the primary to get I2 dash, I4 dash and I3 dash. So what I'm saying over there overall is anything that any values that you know or don't know can all be shifted from the secondary side to the primary side of the transformer using those formulas we used earlier, yeah, and the transformer ratio. So what we've effectively done is made the circuit look like this. Here's our EG onto the main terminals of the transformer. We've got I1, which is a primary side current anyway, flowing there through that impedance Z1, yeah. And then this is where the switch is to secondary side components. So here we've got the value B2 dash that we transferred across, and then there was an impedance there, another one there, and another one there, weren't there? Yeah. And that was Z2, but then we call it Z2 dash now, Z3 dash, and Z4 dash. Yeah. And then current wise, down here, I2 dash, oh no, that was I2 dash there. This is I3 dash, and this is I4 dash. And then our secondary, our transformer is almost redundant in there. So now we've got everything onto one side. We can use values that we know, like the generator voltage and other currents that some of those we transferred over might be known values. To calculate the unknowns here, so we might calculate what Z3 dashes, Z2 dashes, what I3 dashes. When we know them here, we can transfer them back to the secondary using the reverse formulas and find out what their actual values here are. Okay, and as you'll see, you'll be able to solve problems you wouldn't be able to solve if you didn't do transferring impedances. That will all become much clearer when we do an actual example with some values. Yeah. Okay, so the point is we've got every component on one side, and then we can just use normal techniques to find out what all these values are, and then transfer them back to the secondary once we've got a value for them. All right? Everybody happy?
Yeah, I think that's going to become more clear when we see an example, and because I'm sort of struggling
Yeah.
to work out why you'd need to do that, but I suppose that you need to see how it's done.
Yeah, yeah. Right. So let's have a look at one then. Just give some components some values. We'll call this Z1. In my notes, I've got a much easier example. Should I do that? Yeah, I think I'll do that one first. Just pop back to there. What we've got is we've got a generator connected to 2 terminals of a transformer. We've got 10 ohms. Yeah. We've got a current I1. We'll call this Z1. Then we've got transformer ideal, where I is equal to 5. I2, secondary terminals, V2, and then a load Z2 across it. Yeah. Now, if I told you 500 volts is connected across there, as that stands, you have no way of solving, hang on, this is 5 ohms, that problem, because the circuit loop in the primary side is not complete. You haven't got the current, so you can't find a volt drop across Z1. Yeah. So it's EG 500 volts, Z1 10 ohms, which I've drawn on the diagram, Z2 5 ohms, and the question says find secondary voltage, E2, and the current. Yeah, but you have no way of knowing, there's no way you can do that at this moment in time, because you don't have, if you had the current I1, you could find the volt drop across Z1, and then you'd know the voltage here. Yeah, understand that? And then you'd be able to apply the transformer ratio to get the voltage here, and you can solve it. But because you don't, you need to move everything over to the primary side to be able to solve this problem. So our first job here is to find Z2 dash, i.e. what value of impedance is reflected to the primary side. As A squared times Z2, which is 5 squared times 5 is 125 ohms. Yep. So Z2 dash is 125 ohms. We also need to transfer E2. That is I times E2, 5. We don't know, we haven't got a value for E2, but we're saying that we know that reflected voltage is going to be the ratio times E2, yeah, and I2 dash is equal to I2 over A. Again, at this stage, we don't know what that is. All right, everybody happy with that?
Mm-hmm.
So on my next page, what I can then do is draw that circuit out again. Hang on, I'm going to cheat a little bit. So what we can do with that now is take this away for a minute. We've still got those, yeah, but we can put in here 2 terminals and say the voltage there is E2 dash, the current here is I2 dash, and the impedance connected is Z2 dash. Yep. Happy?
Yeah.
And that Z2 dash is equal to 125 ohms. The effectively making the ideal transformer redundant at this stage. What can we now do that will help us solve that problem?
So you can just treat that like a normal circuit now and work out if you find out the total impedance, you can then get the Z1, can't you?
Yeah. So the total impedance seen by the generator is Z1 plus Z2 dash. Agreed?
Yep.
They're just in series.
In series.
Yeah. That's equal to 10 plus 125 with 135 ohms. Yep.
Yep. Can we call that ZG?
Yeah, because I just called it that because that's the impedance seen by the generator.
Oh, okay, right.
Yeah, it's the impedance that the 500 volts of the generator sees.
Okay.
You can call it what you like, really, as long as that's clear what it is.
Yeah. Dave.
All right.
Yeah.
And then what does that mean we can now calculate?
So you can now get the current by going.
Yeah, and if you look at the circuit, we can find I1, which is also I2 dash. They are the same current. If you look up the top line here, I1 and I2 dash are exactly the same current going through the same wire. So we can say I1, which is equal to I2 dash, is equal to ZG, sorry, not ZG, EG, or E1. What do we call it? Do we call it E1 or EG? EG
on there.
of a ZG. That is 500 over 135 equals, I got 3.7 amps, but just check it.
Yeah, 7 point. Yeah, 3.7.
Yep.
Yep.
Now we know that current. What else can we find?
So you could work back now to find I2, or you could. Are you suggesting that we then find the volt drops?
Well, yeah, I mean, you could transfer back the current back and find the voltage, or you could find the voltage E2 dash and then transfer that back.
Yeah.
Either way, you should come up with the same answer. So we can also now, because we know the current going through Z2 dash, we can find E2 dash.
Yeah.
Well, a lot depends on how many unknowns there are that you've got. But E2 dash must be I2 dash times Z2 dash. Yeah, that's 3.7 times 5. Oh, no.
125. Yeah.
That's 3.7 times 125. Yeah.
Yeah.
Equals 92.6 volts. Isn't it? No, isn't that?
No.
Oh, 400.
No, 463.
Yeah.
Yeah.
Yeah. Now we can go through the process of transferring this current and this E1 I2 dash and E2 dash back to the back to the secondary. Yeah.
Mm-hmm.
So we said that I2 dash was equal to I2 over A. Therefore, I2 must equal A times I2 dash. That's 5 times 3.7 equals 18.5 amps. Yeah. Agreed?
Yep.
And then we also said that E2 dash was A times E2. Therefore, E2 must equal E2 dash over A, which is 463 over 5
That's what
equals 92.6 volts. Yeah, I was looking at the wrong part of the screen. All right.
Yep.
So whereas if this problem was originally just a normal ideal transformer problem without that Z1 being in there, you put 500 volts in and expect to get a fifth about 800 volts. But because we got that resistance in the primary winding, we're putting 500 volts in and getting 92.6 volts out. But without transferring those impedances, you didn't have enough information to be able to find the current in the primary, and therefore you couldn't find the current in the secondary. Yeah. Okay.
Yep.
Yeah, that wasn't as bad as I thought, to be fair.
Right. So let's have a look what else we got on the pages that you've got here. So skip over that one for a minute. Yeah, we'll have a quick look at this. I'm just going to turn the light on. It's equally valid, and we're going to have to deal with a situation where we haven't just got pure resistances, because we're going to have to take into account, we're going to have the inductance of the windings and maybe capacitance involved as well. Yeah, which means the maths gets a little bit more complex, because we have to take the angles into consideration. Yeah. So we'll start a new meeting up, because this one's nearly finished, and then I'll come back to this problem. All right.
Mm-hmm.
Yep.